All right, start. Good afternoon, my name's Chad Duty. I'm from the Mechanical Engineering Department at UT, and I have the privilege of doing research on 3D printing. And I know many of you have done 3D printing. I'm really surprised at the amount of 3D printers that are on campus. You get to do mechanical objects, art, and who hasn't printed a Yoda head, right? I mean, that's the first thing you gotta do. Well, I have the privilege of working out at the manufacturing demonstration facility with Oak Ridge, and we invented the BAM system, the largest 3D printer in the world. It would barely fit in this room. And what do you print with a big printer? Every guy likes to play with cars, right? So we printed cars. We had the first 3D printed car, the Shelby Cobra. Looks really amazing. And it's really awesome. If you're not familiar with 3D printing, you design a part in CAD. You create a beautiful drawing, geometrically complex, and then the first thing that you do to 3D print it is you slice it virtually into layers, and then the printer prints it up layer by layer by layer, which is great, and it's a great technology, but what that creates is you're not really doing 3D printing, you're actually doing 2.5D printing because you're doing one pattern, one pattern, one pattern, one pattern. It's kind of like stacking up paper, and if you take a cross-section of the part, you see that same layered that layered pattern going across your part on the inside. Well, what does that mean? Us mechanical engineers, we have a word for that called anisotropy. It's a fancy word. Basically what it means is if you pull on it in one direction, the mechanical properties are different than if you pull on it in another direction. If you've ever seen a broom or felt, everybody's done this, right? You pull it across one way, it's weak. Pull it across another, it's strong. If you've ever split wood, you know it has a natural grain. The same thing happens with 3D printing, and if you played around with it long enough, you know that it happens. If you look at our beautiful car, that was the one we did at the show. This is the one that we did the first print, and it cracked. It was awful. It cracked right along those layers of paper, okay, that we generated. So what do we do with that? Does that mean that 3D printing is useless? No, it doesn't mean that 3D printing is useless. It means that we just have obstacles that we need to get around. And every manufacturing technique has these type of challenges. Everybody knows once you know the strong direction, you can design for that. You can work around that problem. So that's just a standard challenge. If you even look at standard products that you use every day, a cup, a golf ball, a toothbrush, these are standard things that are injection molded, and even they have those same type of issues. Looking at an injection molding process, we're using polymers, thermoplastics, that sort of thing. Now, as a dumb old mechanical engineer, we look at polymer chains as spaghetti. And I know I just offended all the chemistry people in the room, right? But that's the way we think about them. And if you flow these long polymer chains, they tend to flow align. They align with each other. So as you're injecting them into these processes, all those polymer chains are aligning with one another and creating that natural anisotropy. So if we look at things like soda straws, extruding them, if you ever play with Play-Doh, the extruder, it's the same process. We just do it with hot plastic. All those polymer chains, those spaghetti strands, line up and they create a natural weak section there. So if it busts, if a pipe busts or a soda straw busts, that's where it's going to break. If you take something a little more complex, like a cup, it's got a little belly button in the bottom. Now these are not the cups you're drinking out of tonight, so don't do them for these. It has so those polymer chains will do a starburst in the bottom and a line up the side. So as we're looking at that and understanding the mechanical properties of even a simple thing that's conventionally made like a cup, we need to think, okay, if we put this thing under stress, how is it going to break? Now, as mechanical engineers, it's like the best job ever because we get to break things and we get paid for it. It's awesome, okay? So if we take something simple like this and we actually break it, we should be able to put some force on it and pop that thing, and sure enough, if the folks up front can see, it goes right down the line and it goes right along that starburst pattern in the bottom and stops at the belly button, okay? Any product that you make conventionally has anisotropy based on the way it was manufactured. So we need to design for that and account for that. Okay, so now if we get back to 3D printing, my car is cracking apart, right? I've got it just slitting along those lines of paper. If you ask any third grader, you got a stack of paper, how do you join them together? They're going to go over to their desk, and what are they going to pick up? A stapler, okay? I can put these things together. So you take that little elementary thought and you bring it up to the graduate research level, and we invented and have actually patented this process. If you look at the cross-section of it, we leave holes in the 3D printed part, and then as we're printing, we'll come in and we'll fill those across layers. So basically we're putting pins or staples into those sheets of paper. And it drastically improves the mechanical performance because now you're dealing with a stack of paper that's stapled together. If you look at this example, you're looking at the orange kind of paper, those layers of the process, and we've inserted those pins in black going through the layers. And you can see they're nicely mechanically involved with the surrounding paper, so they provide mechanical support. So as we're stressing this material, when we break it, and again, we get paid to do this, it's awesome, the crack goes across the surface, and as you can see, those pins are colored there. As when it hits a pin, that crack will move and use up energy to go in a different direction. So that's adding mechanical energy to try to crack that same part, which gives us better performance. Not only are we stronger, but we're also tougher, and those are different things, right? Strength is how much force it takes to break something. Toughness is basically how much energy that part eats up in order to break it. So if we're twice as tough, we're making a much better part, and that car now doesn't crack, right? So if we look at it, this is not only useful for combining materials that are the same, but you can start now thinking about, okay, what if I want to combine materials that don't naturally like each other, like oil and water? How do I start getting those to bond together? And we can use our stapler to do that. So there's a lot of opportunities here. The great thing is, this is only a software update. So you people who think you've been doing 3D printing, sorry to say you've only been doing 2.5, but with a software upgrade, someday soon, hopefully you'll be using your printer to do actually 3D printing. And that's a bunch of the guys that actually did a lot of the work. So thank you very much. I appreciate your time.